All right, so last time we learned about the general properties of acids and bases. We learned that acids have sour taste and that they turn litmus paper red, whereas bases have bitter taste and that they turn litmus paper blue. We also learned about the different definitions of acids and bases. We talked about two different definitions out of three. There's the Arrhenius definition of acids and bases, which means that an Arrhenius acid is an acid in which it produces a hydrogen ion, right, called a proton. And an Arrhenius base is the one that produces a hydroxide ion, OH minus. The second definition is called the Bronsted-Lowry definition. So Bronsted-Lowry acid is an acid in which it donates a proton, right, a hydrogen ion. And a Bronsted-Lowry base is the one that accepts that proton or hydrogen ion. And we also learned about a class of compounds called alkaloids, right? And alkaloids are organic compounds that have properties similar to a base. So they have basic properties. And a lot of these compounds are often poisonous, right? They're toxic. So for example, quinine, we talked about quinine, which is the compound that basically killed Socrates, right? It's present in the plant called poison hemlock. And there are definitely other types of alkaloids that are also poisonous, such as cocaine, ephedrine, morphine, nicotine. So these are compounds that are toxic at high concentration. We also learned about different types of acids and bases, right? There are weak acids and bases. There are also strong acids and bases. And there are several ways how we can determine the strength of these acids and bases. One is looking at their ionization constant, right? Ionization constant is basically the same as an equilibrium constant, except it's in terms of an acid or a base. So Ka is the equilibrium constant of an acid, or ionization constant for an acid, and Kb is the base ionization constant or the equilibrium constant for a base. The other way of determining the strength or quantifying the strength of acids and bases is looking at their pH and pOH values, right? So if the pH is greater than 7, then it is basic. pH that's less than 7 is considered acidic, and pH equivalent to 7 is considered neutral. And pOH is similar, right, with a few differences. So pOH equivalent to 7 is considered neutral, but pOH that's less than 7 is considered basic, and anything greater than 7 is considered acidic. All right, and then so in this lesson, we'll learn about two other ways of determining the strengths of acids and bases, and we're also going to look at how we can determine the pH of a mixture of acids. Let's say we have a mixture of a strong acid and a weak acid. How would you determine the pH? Or if we have a mixture of two weak acids, right? A mixture of weak acids. How do you determine the pH? And so a lot of these problems are basically equilibrium type of problems where you set up your istable. And the last part of this lesson is going to be regarding equilibrium and weak bases. So we calculate the pH or the pOH of the solution containing weak bases by solving an equilibrium problem similar to a weak acid. All right, so another way of looking at the strength of acids and bases is to look at their pKa values and the pKb. So in the previous lesson, we learned that the letter P in pH and pOH means that it's a mathematical operator, right? If you put a P in front of anything, pH, POH, it means you're taking the negative log of that value, right? So pH means you're taking the negative log of the concentration of the hydrogen ion or the hydronium ion, and POH is the negative log of the concentration of OH minus or the hydroxide ion. And so pKa means that you're taking the negative log of the Ka. And Ka is the ionization constant for an acid. And pKb is the negative log of Kb, which is the ionization constant for a base. So again, pKa then is the negative log of Ka, and pKb is the negative log of Kb. And so the smaller the value of pKa, the stronger the acid. The reason why is because if Ka is large, that we know that it's a strong acid, right? And so when you take the negative log of a large number, then it becomes a smaller number. Okay, and if you take the negative log of a small number, you get a value that's larger than the original number. Okay, so they're inversely proportional. So again, the smaller the pKa, the stronger the acid, and the larger the Ka means smaller pKa. Okay, and in terms of bases, the smaller the pKb, the stronger the base, and that's because the larger the Kb value, the smaller the pKb. Right, and so it goes the same way for Kb, right? So the larger the Kb value, the stronger the base. All right, so here's a table that basically lists weak acids, and you've seen this in the previous lecture. So you have chlorous acid, right, listed at the very top, and this is basically the strongest of the weak acids listed here. You can see that the Ka value here is the largest, right, with 1.1 times 10 to the negative 2. And when you take the negative log of this value, negative log of 1.1 times 10 to the negative 2, you get a pKa value of 1.96. Okay. Now, if you compare chlorous acid with another weak acid, a weaker acid, down here at the bottom, benzoic acid, right? You can see that the Ka value is lower than that of the chlorous acid. So the Ka value is 6.5 times 10 to the negative 5. And so you know that it's a weaker acid. But when you take the negative log of that number, negative log of 6.5 times 10 to the negative 5, you get a pKa value of 4.19, which is larger than the pKa of the chlorous acid. So if you're comparing two pKa values, the larger pKa is the weaker acid, and the smaller pKa is the stronger acid. Okay, so how do we find the concentration of hydronium ion and ultimately the pH of an acid solution? So remember that the formula for pH is negative log of the concentration of hydronium, H3O+. So for a strong acid, the hydronium concentration is equivalent to the given concentration of the acid, which makes sense because strong acids ionize completely in water. So what that means is that it dissociates into ions 100%. Right? So for instance, if we have hydrochloric acid, right, and you dissolve this in water, we get H3O plus and the conjugate base, chloride ion. Right? So that means that if you have 1 molar of this hydrochloric acid, it will generate also 1 molar of the hydronium ion. Right? And we're using a single arrow here because of the fact that it only goes in one direction. Right? It goes in the forward direction. So another example is if you have nitric acid, right, HNO3. So when you dissolve this in water, you generate the hydronium ion, H3O+, and the conjugate base, which is the nitrate ion. It's a conjugate base because it can accept a proton, right? And proton is a positive charge. You can see that the nitrate ion has a negative charge, and so you can tell that it has the ability to accept a proton. So if you remember, according to the Bronsted-Lowry base definition, a base is one that can accept a proton, right? And one of the conditions is that that molecule or ion has to have a lone pair of electrons in order to be able to accept a proton. All right, so in this example, for strong acid, if you have a 1 molar nitric acid, then that will generate the same concentration of hydronium ion. So that means that your nitrate will also have a concentration of 1 molar, right? If you remember from Chemistry 1311, General Chemistry 1, this is a 1-to-1 mole ratio. So that means that 1 mole of nitric acid will generate 1 mole of hydronium ion and 1 mole of nitrate ion. So it's the same concept here when it comes to molarity, the concentration. All right, so let's look at an example here. So for instance, we have 0.10 molar hydrochloric acid. So that means that it will contain, or it will generate 0.10 molar concentration of hydronium ion, because again, that's a 1-to-1 mole ratio. So because we know the concentration of the hydronium ion, we can calculate the pH of that acid solution. So pH is equivalent to the negative log of the concentration of the hydronium ion, and we get negative log of 0.1, we get pH of 1.00. What about for a weak acid? How do we determine the concentration of the hydronium ion and ultimately the pH of that solution given the concentration of the acid, right? So we know that for weak acids, they don't ionize completely in water. They only ionize partially, about 1 to 2%, okay? Compared to a strong acid, which ionizes completely at 100%. So for weak acid, the hydronium acid concentration is not equal to the given concentration of the acid. So again, for instance, if we have nitric acid, or nitric acid is a strong acid, acidic, let's say formic acid. So formic acid is HCHO2, right? And if you ionize this in water, H2O, it doesn't ionize completely. So that means it's going to reach equilibrium at some point, right? So we use this double arrow. So you'll get the same products, H3O plus the conjugate base. In this case, it would be CHO2 minus. Right? You just subtract that hydrogen here to get CHO2 minus. And so if you have 1 molar solution of the formic acid, that means that the concentration of the hydronium ion will be a lot less than 1 molar, right? Based on the definition of a weak acid. They don't ionize completely, so they don't generate the same concentration of hydronium ion. So if we're looking at 1% ionization, so that means that the concentration is probably going to be around 0.01, right, or 0.001. All right, so let's look at a comparison here. So let's say we have 0.10 molar acetic acid, HC2H3O2, right, and compare that with the pH of a strong acid, hydrochloric acid. So in this case, we have 0.10 molar hydrochloric acid with a pH of 1.00, which is what we calculated earlier. As you can see here, the pH of the weaker acid is higher, right? 2.87. And we know that the lower the pH, the more acidic the acid is, right? So for the acetic acid, pH is 2.87, and that's because of the fact that it didn't generate the same amount of hydronium ion compared to the hydrochloric acid. So the acetic acid here has a larger pH because of the fact that it's a weaker acid. It didn't generate enough hydronium ion, so it has lower hydronium concentration. And we know that for a fact that weak acids only ionize partially, about 1 to 2%. And that's why the pH is greater than the strong acid, hydrochloric acid. All right, so how do we find the pH of a weak acid then, right? And because we know that weak acids don't dissociate completely in water, it's going to reach the equilibrium at some point, right? So we have to use the equilibrium symbol here. Calculating the concentration of hydronium ion requires solving an equilibrium problem for the reaction that defines the acidity of the acid. So the first thing that you want to do, if you're given the concentration of the acid, for example, here we're given 0.10 molar of acetic acid, HC2H3O2. So the first thing that you want to do is write the reaction equation. So when you're writing the reaction equation, you're always reacting that acid with water, H2O, as you can see here. Right, so when you react an acid, a weak acid, with water, you'll always generate two things. One is the hydronium ion, right? And the other one is the conjugate base. Again, it's a conjugate base because it can now accept a proton. Again, by Bronsted-Lowry definition of a base, it can accept a proton in the reverse direction. All right, so in order to determine the pH, we need to determine the concentration of the hydronium ion, H3O+, at equilibrium. So in order to do that, we have to set up an ice table. So here's the ice table, and we're going to populate this ice table. So we're given the initial concentration of the acid here. And so the initial concentration then is 0.10. All right, and you've seen equilibrium problems in the previous chapter, right? Chapter 15. And so initially, the concentration of the products will be 0. And the change here, so because the reaction will shift from right to the left towards the products, the acetic acid here will receive a negative change, right? So it'll have a negative X, and then the products will receive positive X. Okay? And then you perform mathematics here, and you get 0.10 minus X at equilibrium. So this is the concentration at equilibrium as a function of X. All right, and then you set up your Ka expression. So normally whenever you're finding the pH of a weak acid, you'll be given the value of Ka. So that's one of the requirements. In order to find the pH of a weak acid, you have to be given at least two informations. It could be the concentration of the acid and the Ka. Okay? So the Ka expression for this is the concentration of the products. So that would be H3O+ at equilibrium times the concentration of conjugate base divided by the acid itself, right? And so we plug in the equilibrium concentrations as a function of X into the Ka expression. So then this is equivalent to x times x divided by 0.10 minus x, which gives you x squared divided by 0.10 minus x. So when you have a Ka value here, then you'll be able to solve the value of x. Okay, either using the approximation method that you learned in chapter 15 or the quadratic formula. All right, so here's a cleaner version. All right, so here's an example. Find the concentration of the hydronium ion of a 0.100 molar hydrocyanic acid with a Ka value of 4.9 times 10 to the negative 10. All right, so the first thing that you want to do here is to set up your reaction equation. Right, and HCN reacts with water. And we know it's a weak acid because the Ka value here is less than 1. So we'll use the equilibrium symbol here. And this always gives you the same products, the hydronium ion and the conjugate base. Right? When you're determining the conjugate base, all you have to do is remove the hydrogen from the acid and give it a negative charge. So that would be Cn minus. Okay, and then you set up your Ka expression, right? So Ka equals the concentration of the products raised to their coefficients divided by the concentration of the acid. So the reason why we're leaving H2O out of the equilibrium expression is because this is a liquid. So if you remember from the previous chapter, we omit liquids and solids. So we only include aqueous and gases, right? So for the rest of these, they're all in aqueous state, right? Aqueous solution, because you dissolve them in water. All right, so this is equivalent to 4.9 times 10 to the negative 10, the Ka value. And so now you have to set up the ice table, right? Because this is an equilibrium problem. So we have HCN, H3O plus, and the conjugate base, Cn minus. So we're given the initial concentration, which is 0.100. And initially for the products, 0. And the change here then will be negative x for the reactants and positive x for the products. And then we find the equilibrium concentrations as a function of x. And now we plug this into the Ka expression. Right, so we have 4.9 times 10 to the negative 10 for the Ka value, and this is equivalent to x times x divided by 0.100 minus x. Okay, and here's the shortcut. When you see that the Ka value is less than 10 to the negative 3, if you see that if the Ka value is less than 1 times 10 to the negative 3, you can drop the x, right? So we can use the approximation method. So that will simplify the math by a whole lot, okay? So then you do the math here. So we have 4.9 times 10 to the negative 10 multiplied by 0.100 equals x squared. Okay, and then you can just take the square root of both sides in order to get the value of x. So x equals the square root of 4.9 times 10 to the negative 10 times 0.100. So make sure that whenever you're plugging this into the calculator, that you enter all the numbers in parentheses, right, inside of the square root. So here we get a value of x equal to 7.0 times 10 to the negative 6. Okay, so this is the concentration of the hydrogen ion or hydronium ion. Okay. So from here you can even determine the pH of this solution by plugging in this value into the equation for pH, right? So we know that pH equals the negative log of the H3O plus concentration. So when you plug this into the calculator, negative log of the concentration, we get 5.15 as the pH. Here's a cleaner version. So set up your reaction, populate the ice table, write the Ka expression, and solve for x. And if you're going to use the approximation method, make sure that you validate the approximation. So you can validate it by dividing the value of x that you calculated by the initial concentration of the acid, which is 0.100, multiplied by 100%. So if the percent is less than 5, then it's valid. Otherwise, it's invalid. All right, so here's an example of when the approximation doesn't work. So you can see that the Ka value here is 0.011, right? And you can see that that's greater than 1 times 10 to the negative 3, right? So we shouldn't be using the approximation method in the first place because the Ka value is greater than 1 times 10 to the negative 3. So what we're going to do here is we're not going to use the approximation method. So instead, we're going to use the quadratic formula to solve the value of x. So again, in order to find the pH of a weak acid, again, you can see that it's a weak acid because it's less than 1. The Ka value is less than 1. So we're going to have to solve this using the ice table. But first, we have to write the reaction equation for this acid. So we have HClO2. Again, you're reacting it with water. Equilibrium symbol here. And we get H3O plus the conjugate base. Okay, and then we write the Ka expression. Again, we're going to be omitting water here in this expression. So we have H3O plus concentration times the concentration of the conjugate base divided by the concentration of the acid. All right, and this is equivalent to 0.011. And then we prepare our ice table. So we have HClO2, H3O plus, and our conjugate base. Okay, our initial concentration for the acid is 0.100. For the products, 0. And the change here is going to be negative x for the acid plus x for the products. And then we find the concentration of these at equilibrium as a function of x. All right, So again, because Ka is greater than 1 times 10 to the negative 3, we don't drop the x, right? We don't use the approximation method. So our Ka is 0.011, and that's equivalent to x times x divided by 0.100 minus x, right? And so we move the denominator to the left-hand side by multiplication, so we have 0.011 times 0.100 minus x equals x squared. Then we use distributive property here. 0.011 times 0.1, and then 0.011 times negative x. So we get x squared plus 0.011x minus 0.0011, and this is equivalent to 0. So that's equal to 0. So now we have our quadratic equation, right? So A here is equivalent to 1, B is equivalent to 0.011, and our C here is equivalent to negative 0.0011. And so we can plug this into the equation. X equals negative b plus minus square root of b squared minus 4ac divided by 2a. Okay, and when we plug in these values, you get two values of x. One is going to be less than 0, meaning it's negative, and so we omit this, and the other x is equivalent to 0.028. And so because this is negative, we cross that out, and so our answer is the positive value here. If you get two positive values, you're going to have to check and see which one is the valid one, right? By plugging it in to the equation for equilibrium and see which one makes sense. All right, so because this is the value of x, this is also the concentration of the H3O+, right? And so pH is equivalent to the negative log of the concentration, which is 0.028, and the answer is 1.55. So we have a pH of 1.55, which is still considered acidic, but it's a weak acid. Here's a cleaner version. Set up the equation and the ice table, and then populate the ice table. Generate the Ka expression. So this calculation shown here right now is using the approximation method, and you can see that it's invalid because when you validate it by dividing it by the initial concentration of 0.1 times 100%, you get a value that's greater than 5%. So this is considered an invalid approximation, and so you're gonna have to use the quadratic equation as shown here, and we get a value that is less than 0, negative, and the other one is 0.028. And so we drop the x and use the positive value here. Plug it into the equation for pH, and we get pH of 1.55. All right, what if we're given the pH of a solution instead of the Ka? Right, so we're given two information here, right? One is the concentration of the weak acid and the pH. So we're given the pH instead of the Ka. So how do we find the equilibrium constant Ka given the pH and the concentration of the acid. So we're going to do the same thing. Because this is a weak acid, we're going to have to use the ice table. The very first thing you want to do is to write the reaction equation. So for a weak acid, again, HA plus water, and we get H3O plus and the conjugate base. Okay, and then our Ka expression is H3O plus concentration times the conjugate base divided by HA concentration. All right, and this is what we're trying to find. We don't know what it is, but we're given the pH. So we set up our ice table. So we have HA, H3O plus, and the conjugate base. We're given the initial concentration of 0.1 for our products initially 0. So because we don't know the Ka value, we don't know whether we're going to drop the X here, right? We don't know if we're going to use the approximation method because we're trying to find Ka. All right, so we plug this in to the Ka expression, right? But first, we have to determine the concentration of the hydronium ion, right? And we can determine the concentration of the hydronium ion from the pH. If you remember, pH is equivalent to the negative log of the hydronium concentration, right? And so we can isolate the concentration by simply raising 10 to the negative pH. So that's how you get rid of the log function. Okay, so the concentration that we get here is the concentration at equilibrium. And so if we plug in 10 to the negative pH, which is 4.25, we get a value equal to 5.62 times 10 to the negative 5. So this is the concentration of H3O plus at equilibrium, which means that it's also equal to the value of X here. Right? So now that we know the value of X, we can find the Ka. Right? We can just plug in 5.62 times 10 to the negative 5th to the x's here. Right? And we know the Ka expression. Ka equals x squared. Right? So that's 5.62 times 10 to the negative 5th times itself divided by 0.100. Minus x, minus 5.62 times 10 to the negative 5th. So because this number, x, the value of x here, 5.62 times 10 to the negative 5th, is so much lower than 0.100, you don't have to include it in this calculation here. Right? You don't need to include this in the denominator, because it's such a small number that subtracting it from 0.100 makes it insignificant. And so you can just leave it out. So solving for Ka here, plugging it into the calculator, we get a value of 3.16 times 10 to the negative 8. Okay, so this is our Ka value. And remember that Kas and Kbs, right, any equilibrium constants, they don't have a unit. All right, so here's again the cleaner version. So populate your ice table and then solve for Ka, which is 3.1 times 10 to the negative 8. All right, so we looked at the pKa values, we looked at the pKb's, the equilibrium constants Ka and Kb in determining the strength of the acid. Another way to determine the strength of the acid is by looking at percent ionization. So we learned earlier that hydrochloric acid ionizes 100% in water, whereas weak acids, they only ionize partially, about 1%. So that means that the higher the percent ionization, the stronger the acid. So the concentration, the equation for percent ionization here is the concentration of the ionized acid divided by the initial concentration of the acid, right? So when we say concentration of ionized acid, that means is the concentration of the hydronium ion at equilibrium. Okay, so it's H3O plus concentration at equilibrium divided by the initial concentration of the acid times 100%. All right, so here's an example. Find the percent ionization of a 2.5 molar nitrous acid solution with a Ka value of 4.6 times 10 to the negative fourth. Right, so we know this is a weak acid because, again, the value of Ka is less than 1. And so for every weak acids, you would have to use the equilibrium symbol. So again, this is going to be an example of an equilibrium problem. So the first thing you want to do is write down the reaction equation. So we have HNO2 plus water and we get H3O plus the conjugate base, which is NO2 minus. All right, and then you prep your ice table. Okay, so we're given the initial concentration here, which is 2.5. So we are prepping an ice table here because in order to find the percent ionization, we need the concentration of the hydronium ion, H3O plus. And in order to find the concentration, we have to use the ice table. All right, so again, initially we'll have 2.5 molar of the nitrous acid solution and 0 for the products. And then the change would be negative x here and plus x's. And 2.5 minus x, x, and x. All right, and then we generate the Ka expression. Ka equals H3O plus concentration times the concentration of the conjugate base divided by HNO2. All right, and we're given the Ka value here, which is 4.6 times 10 to the negative fourth. And so plugging in the equations for equilibrium here as a function of x, we have x squared divided by 2.5 minus x, but we're dropping the x because the Ka value is less than 10 to the negative 3. So make this equal to 4.6 times 10 to the negative fourth and solve for x. So you can see that x equals 4.6 times 10 to the negative fourth multiplied by 2.5, and then you take the square root. So plugging it in to the calculator, we get a value equal to 0.0339. So this is going to be the concentration of the hydronium ion, right? It's equivalent to X at equilibrium. So in order to find the percent ionization, set this equal to the calculated value of hydronium at equilibrium divided by the initial concentration, which is 2.5, multiplied by 100%. And this gives us 1.36% ionization. So you can see that a large majority of the acid is still in the HNO2 state, right? They're still intact. Only about 1.36% were converted into the hydronium ion. Only 1.36% were ionized, right, in water. So you can tell that it's a weak acid. So you already know it's a weak acid, right? 4.6 times 10 to the negative fourth. But what if you don't have that information? What if you're given the percent ionization? Then you should be able to also determine the strength of that acid. Okay, so 1.36% means it's a weak acid. Here's a cleaner version. All right, so what's the relationship between the concentration of the hydronium ion at equilibrium and the initial concentration of the acid, right, in terms of percent ionization and concentration of the hydronium ion? So basically, what happens to the percent ionization if you were to increase the concentration of the acid? What happens to the concentration of the hydronium ion if you were to increase the concentration of the acid? All right? So increasing the initial concentration of weak acids results in the increased concentration of the hydronium ion at equilibrium, but decreased percent ionization. So that means that if you were to increase the concentration of the weak acid, you're actually lowering the percent ionization, the overall percent ionization of that acid. Because again, the formula for percent ionization is the concentration of the hydronium ion divided by the initial concentration. So increasing that denominator, right, the concentration of the weak acid, will generate a lower percent ionization because you're not getting enough of the concentration of the hydronium ion. So here's an example. Which weak acid solution has the greatest percent ionization? And which solution has the lowest, most acidic pH? All right, so we're going to answer the second question first. Which solution has the lowest, most acidic pH? So the one with the lowest pH, right, the most acidic, is going to be the one that will generate the most hydronium ion, H3O+, because pH is equivalent to the negative log of the concentration of the hydronium ion. So the greater the number, the higher the concentration of this hydronium ion, the lower the pH, because you're taking the negative log of it. So right off the bat, you would have to pick the one with the higher concentration here, which is B for the acetic acid, 0.500 molar acetic acid. So that will generate the most hydronium ion, because the choices here, they're all the same acid. It's acetic acid, so they will have the same Ka value. The only difference here is the concentration. So we know that concentration of the hydronium ion is directly related to the initial concentration of the acid. So in terms of percent ionization, we would have to pick the one with the lowest concentration, because that will generate the highest percent ionization. Okay. So for the first question, it will be C, the answer, lowest concentration. And the one with the lowest pH would be the one with the greatest concentration, initial concentration, which is B. All right, so how do we find the pH of mixtures of acids? So what we've looked at so far is finding the pH or the concentration of the hydronium ion of just one acid in solution? What if we have a mixture, right? So there are two scenarios here. One is a mixture of strong and weak acids. And the other scenario here is if we have both weak acids. Okay, so whenever we're determining the concentration of the hydronium ion, we ignore the ionization of the weak acid initially for that mixture. Okay, and we'll look at an example for this on the next slide. But if we have a mixture of both weak acids, we ignore the ionization of the weaker acid completely whenever we're calculating the concentration of the hydronium ion for that mixture, as long as two conditions are met. The first one is as long as the Ka value is 100 times greater than the Ka value of the other acid. Okay, meaning one acid is 100 times stronger than the other acid. And two, their concentrations have to be similar, somewhat similar, right, in order to be consistent in comparison. So let's look at an example here between a strong acid and a weak acid. Consider a mixture of 0.10 molar hydrochloric acid and 0.10 molar formic acid. So here formic acid is the weak acid, hydrochloric is the strong acid. And we're given the Ka value here of formic acid. Okay, because the Ka value of hydrochloric acid is a lot greater than 1. It's actually in the millions. How do we find the concentration of the conjugate base, formate ion, CHO2 minus? All right, so we're going to write the equation, the reaction equation for the strong acid first. So we have HCl, right, plus H2O, single arrow, and you get H3O plus the conjugate base, chloride ion. And the Ka of this is a lot greater than 1. Okay. And for the weak acid, we have formate ion, formic acid here, HCHO2 plus H2O, double arrow, H3O plus Cl minus. And the Ka is given here, which is equivalent to 1.8 times 10 to the negative 4th. So here we're given the concentration of the strong acid, hydrochloric acid, 0.10. So that means that the concentration of the hydronium ion is also going to be 0.10 molar. Okay, and so when we mix the weak acid with the strong acid, there's already an existing amount of the hydronium ion. And so we can calculate, it looks like I made a mistake here. I'm going to erase the conjugate base of the formic acid. So this is supposed to be CHO2 minus. All right, so in order to find the concentration of the formate ion, CHO2 minus, we have to generate an ice table for the weak acid. Okay, and we're going to generate a Ka expression for the weak acid as well, because we're given the Ka expression here. So the Ka expression for the formic acid is H3O plus times the concentration of the conjugate base, which is CHO2 minus, divided by the concentration of HCHO2. And this is equivalent to 1.8 times 10 to the negative 4th. Okay, and then we're going to set up our prep table. right? So we're given the initial concentration here for the weak acid, which is 0.10 molar. And because there was hydrochloric acid in the mixture, we already have an existing concentration of the H3O plus. So initially, we will also have 0.10 here for the concentration of hydronium ion initially, and then 0 for the conjugate base. And then you would proceed normally. So we have minus X here, plus X, plus X. All right, and so we have the Ka expression, 1.8 times 10 to the negative fourth. And because the Ka value is less than negative 10, it's less than 1 times 10 to the negative 3, we can drop the X here, right? So this X right here will be dropped, and this X right here will be dropped in order to simplify the mathematics. So we're going to plug this into the expression. So H3O plus concentration at equilibrium is 0.1 times X divided by the concentration of HCHO2, the forming acid, at equilibrium, which is also 0.10. So as you can see, 0.10 here will cancel, and we get X equal 1.8 times 10 to the negative fourth, which is surprisingly the same value as the Ka. So X is 1.8 times 10 to the negative fourth, which is also the concentration of CHO2 minus, right? So that's going to be the concentration of the formate ion, or the conjugate base. As you can see, you can also calculate the pH of this mixture, right? We know the concentration of the hydronium ion, so pH equals negative log of H3O plus concentration, which is essentially equal to 1.00, which is the pH of the strong acid. So if you were to determine the pH of a 0.10 molar hydrochloric acid, you get the pH also equal to 1. So the hydronium ion, so the hydrochloric acid is dominating the weak acid here, right, in terms of the concentration of hydronium ion. All right, so here's a cleaner version. Okay, so what if we have both weak acids in that mixture, right? So how do we find the pH of a mixture that is 0.300 molar hydrofluoric acid and 0.100 molar hypochlorous acid? So we're given both the Ka values here, and according to the previous slide, we're supposed to ignore completely the Ka of the weaker acid, and we're going to use the Ka of the stronger acid, in this case the hydrofluoric acid. So we're going to ignore the second Ka here because it's weaker, and then we would proceed normally using the information we have for hydrofluoric acid. And so we write the reaction equation for HF. Okay, and then we prep our ice table. So the initial concentration of hydrofluoric acid is 0.300, 0 for the products, plus X for the products. And because we're given the Ka value here, again, this is less than 1 times 10 to the negative 3, then we omit X for HF. So we're just reporting this as 0.300 X. And then we generate our Ka expression, so that would be H3O plus times fluoride ion concentration divided by HF. And this is equivalent to 6.8 times 10 to the negative fourth. That's equivalent to x times x, which is x squared, divided by 0.3. All right, and then you can isolate x by taking the square root of the product of Ka and 0.3. And so we get a value for x equal to 0.0143. Okay, so this is the concentration of H3O plus. We can find the pH by plugging in this value to negative log of 0.0143. And we get a pH of 1.85. Here's a cleaner version. So again, if you're going to use the approximation method, make sure that you validate it. And you can see that it's less than 5%. So it is a valid approximation. So again, the pH that we found here is 1.85. All right, so we're going to make a transition here into strong and weak bases. And the idea here is, of course, similar to the strong and weak acids. So we're still going to be generating and prepping ice tables and Ka or Kb expression for bases. All right, so there's not a lot of difference here. We know that strong bases, similar to strong acids, they ionize completely in water. So they generate the same concentration of hydroxide ion as the initial concentration of the base. And so the stronger the base, the more willing it is to accept a proton. For ionic bases like sodium hydroxide, practically all units are dissociated into hydroxide ion and the cation ion, sodium ion. All right, so if you remember, strong bases are strong electrolytes. So that means that they dissociate completely or 100% in solution. And so make sure that you remember all the strong bases listed here in table 16.7. And if you notice that a lot of these strong bases, they contain the hydroxide ion, OH minus. And so for example, we have lithium hydroxide, sodium hydroxide, potassium hydroxide. And a lot of these hydroxides on the left side of the table are all based off of group 1 elements in the periodic table. And the bases on the right hand side of this table are based off of group 2 elements, right? The alkaline earth metals in the periodic table. So as long as you memorize these 6 strong bases, then you should be fine on the test. So anything that's not included, if it's not one of the 6 bases listed here, will be considered a weak base. All right, so in contrast, weak bases don't ionize completely in solution. So similar to a weak acid. So they only ionize about 1%. So that means that the concentration of the hydroxide ions that are generated is less than the concentration of the weak base itself. So for example, if you have 1 molar of a weak base in solution, you only generate about 1% of that. So maybe 0.01 molar of the hydroxide ion. So finding the pH of a weak base solution is similar to finding the pH of a weak acid. So that means that we're going to generate the reaction equation and we're going to generate an istable. And when we generate the Kb value, right, the equilibrium constant of a base, also known as the base ionization constant, we use the same expression, right, as you would normally for an equilibrium constant. So it's the concentration of the products raised to their coefficients divided by the concentration of the reactant raised to its coefficient. And you want to make sure that you omit any liquids or solids from the expression. So again, the larger the Kb value, the stronger the base. So in this equation here, we have the base, okay, and water is acting as the acid because it can generate, it can donate a proton, and the base will accept the proton and it'll turn into a conjugate acid. And our hydroxide ion here is the conjugate base. Okay. All right, so here's a table listing some of the most common weak bases. And you can see that carbonate ion here is the weakest, or I'm sorry, the strongest base that's listed here. And aniline is the weakest base listed here. So you can tell by looking at the Kb values, right? Carbonate ion has a Kb of 1.8 times 10 to the negative fourth, and aniline only has a Kb value of 3.9 times 10 to the negative 10. And if you notice, a lot of these common weak bases are carbon-based, meaning they're organic base compounds. All right, and a lot of them are weak bases. They have low Kb values. So for example, we have methylamine, ethylamine, pyridine, and aniline. They're all carbon-based, right? Meaning they contain carbons, hydrogens, oxygens, and nitrogens. So in the previous lecture, we introduced a new class of acids, right? We looked at carboxylic acids. So a lot of these carboxylic acids, they have a signature group called the carboxylic acid group, also known as the carboxyl group. Okay, CARBOXYL, carboxyl group. In terms of bases, we're going to introduce the amines, right? So similar to the carboxylic acid group, the amines also have signature group called the amine group. All right, so ammonia has NH3, methylamine has NH2, and pyridine has a nitrogen with a lone pair. So a lot of these amines, they contain nitrogen. All right, and a lot of these nitrogens, they have a lone pair of electrons. So for example, this nitrogen in ammonia contains a lone pair. This nitrogen in pyridine also has a lone pair. And this nitrogen in methylamine also has a lone pair. It's just not shown here. But there is a lone pair of electrons, as you can see here in this ball and stick figure. So here, if you guys have seen Breaking Bad, there is an episode in this show in which Heisenberg himself, or Walter White and his assistant Pinkman, they're rolling a barrel of methylamine. Okay, and apparently methylamine is a precursor to the synthesis of meth. All right, so here's a quick recap of how to determine the conjugate acid base pairs. So NH3 here has a lone pair of electron. So that means it can act as a base, right? And water here can act as an acid. So if you notice NH3 on the reactant side, before the reaction is NH3. And after the reaction, it turned into NH4 plus, right? So that means that it gained a proton. So according to the Bronsted-Lowry base definition, any base is a proton acceptor, right? So this, in that case, is a base. And any Bronsted-Lowry acid is a proton donor. So that means that water here donated one of its hydrogens and turned into a hydroxide. So that means that water is acting as an acid, which then turns into a base after the reaction, and the NH3 turned into an NH4, which now is considered an acid, conjugate acid, and we have a conjugate base. So these right here is one conjugate acid base pair, and these two right here is another acid base pair. Okay, and it's the same thing here for the second reaction, right? So we have H2O turning into an OH minus, so that means this is your conjugate base, and water is acting as an acid, and this structure right here turns into this, so it means this is your conjugate acid, and this is your base. All right, so how do we determine the concentration of bases, right? So it says determine the concentration of the hydroxide ion and the pH of the solution. So looking at these bases right here, KOH and strontium hydroxide. So we have potassium hydroxide and strontium hydroxide. And you can see that potassium is in group 1, strontium is in group 2, and so they're both strong bases, right? And so because they're strong bases, they will dissociate completely in solution. So looking at the first example here, A, we have KOH that will dissociate completely in water, turning into K plus and OH minus, the hydroxide ion. And so 0.225 molar of the strong base will generate the same concentration of the hydroxide ion, because they're 1-to-1 ratio. All right, so that means that we can calculate the pH of the solution. But here we're given the concentration of the hydroxide, and so we can first determine the pOH, which is the negative log of the concentration of OH minus, and that would give us a pOH of 0.648. And in order to determine the pH of the solution, we know that pH plus pOH from the previous chapter, or from the previous lecture, is equivalent to 14. So that means that pH is equivalent to 14 minus the pOH that we calculated, 0.648. And we get a pH value of 13.35. So you can tell that it's a basic solution because the pH is greater than 7. Part B here is a little bit different, right? So if we look at the dissociation of the strontium hydroxide, it looks something like this. So you can see that this is not a balanced reaction, right? We have 2 units of the hydroxide on the reactant side, but only 1 unit of hydroxide on the product side. So that means that we have to balance this reaction equation by simply putting a coefficient of 2 in front of the hydroxide ion. So now you can tell that it's a 1-to-2 ratio. For every 1 mole of strontium hydroxide, you get 2 moles of the hydroxide ion. And so if we have 0.0015 molar of strontium hydroxide, we multiply this number by 2, which is going to be the concentration of the hydroxide ion, which is 0.0030. Now we can find the pOH and then the pH of the solution. So pOH is the negative log of 0.0030, which is 2.52. All right, in order to find the pH, we just subtract this number from 14. So pH equals 14 minus 2.52. And we get 11.48 for the pH. So again, pH is greater than 7, and so it's a basic solution. All right, so what if we have a weak base solution, right, NH3, and you're given the Kb value here of 1.76 times 10 to the negative 5. So we know it's a weak base because the Kb value is less than 1. So we would solve this problem similar to how we would for a weak acid, right? So we have to generate a Kb expression and a prep table or equilibrium table. So for NH3, a weak base, you dissolve this in water, and we get NH4 plus OH minus. Okay, so this is how we can determine the concentration of the hydroxide ion. So you prep your ice table. So we have NH3, NH4 plus, and OH minus. So the initial concentration of the ammonia is 0.100, and initially for hydronium it's 0. Okay, again, because the Kb value is less than 1 times 10 to the negative 3, we can drop this x, right? We're going to use the approximation method. And so your Kb expression is equivalent to concentration of NH4 plus times the concentration of hydroxide ion divided by concentration of NH3. And that's equivalent to 1.76 times 10 to the negative 5. And this is equal to x times x, which is x squared, divided by 0.100. And then you can solve for x. So that's 1.76 times 10 to the negative 5 multiplied by 0.100, and take the square root. So we get an x value of 0.00133. So this is the concentration of the hydroxide ion. So then we can determine the pOH of this. So this is basically the negative log of the number 0.00133. And we get 2.88. The pH then is simply 14 minus the pOH. Which is 11.12. So this is the pH of the solution. Again, it's a basic solution. Here's a cleaner version. Again, if you're going to use the approximation method, you would have to validate it. So again, you get 1.33%, which is less than 5%. So this is a valid approximation. So there are more than one way to determine the pH. So you can use it. You can use this method if you like, where you set the concentration that you found, all right, and you use this information and plug it into this equality. So we learned this from the previous lecture, in which the concentration of the hydronium ion times the concentration of hydroxide gives you the ion product constant for water, Kw, which is equivalent to 1 times 10 to the negative 14. So if you plug in the value of OH minus into this equation, you can determine or isolate the concentration of hydronium ion and determine its concentration. Right, so you divide both sides by 1.33 times 10 to the negative 3, and you get the concentration of the hydronium ion, and then solve the pH using this concentration. And we get the same number, which is 11.12 for the pH. All right, so we'll stop there. And so that means that we're going to have to finish chapter 16 on the next lecture. So there's going to be a part 3.